All right, Mr. Samuels here with a continuation of our discussion of acids and bases. So we learned properties of acids and properties of bases, but we need to make sure we understand what makes them different chemically. We learned that acids create H3O plus hydronium ions when dissolved in water because they donate hydrogens. They have hydrogens to give. Bases are the opposite. Bases accept hydrogen. And if you remove an H plus from water, you're going to end up with OH minus. If you may recall, that ion is called a hydroxide ion. And it's the higher the concentration of hydroxide in the solution that raises the pH and makes your solution more basic or alkaline. Sometimes you'll hear that term used to describe basic solutions. So here, the example here, you have ammonia, which is considered a strong base. What happens is it takes a hydrogen from water, takes that hydrogen, now you've got NH4 plus, this ammonium cation, and what's left with the OH minus is that hydroxide ion we talked about. Now in a strong base, these are substances, strong bases refer to substances that completely ionize, completely dissociate in water. Now, just because you have a strong base doesn't mean you have a highly basic solution. It could be dilute, it could be watered down. And so if you only have a little bit of strong base in a lot of water, it's still not a very basic solution. It's close to neutral. On the other hand, you can have a weak base, but if it's extremely concentrated, then you might still have a fairly high pH. Remember, strong bases refer to the substance's ability to form ions, not the pH of the solution or necessarily the hydroxide concentration. Okay, next thing we need to understand is that acids and bases neutralize each other. How does this work? Well, let's take a look here. If you think about it, it makes sense. If acids donate hydrogen and bases accept hydrogen, oh look, now we're neutral. OH plus H forms H2O. So this is actually really interesting if you think about it. This stuff is some pretty nasty stuff. Sodium hydroxide, holy wow. That stuff at a high concentration, sodium hydroxide could burn your skin right off. Similarly with hydrochloric acid. All right, two really dangerous substances when they're in high concentrations. But you combine these two guys and you get, wait, NaCl, that sounds familiar. Salt. Wait, hold on a sec. Mr. Samuels, you're trying to tell me that if we combine two of the most deadly substances around, you get salt water? Yeah. It's pretty wild, but be careful. This is only if it's in the specific right amounts. I don't recommend trying to drink this solution because it might not be quite neutral. Okay, now how to measure how close to neutral we are is a scale called the pH scale. This measures how acidic or basic a solution is. Neutral solutions, by definition, have a pH of 7. This is right in the middle, neither an acid nor a base. That salt water we mentioned before would be a neutral solution. It would have a pH of 7. Acids have a pH below 7, going all the way down to 0, and bases have a pH above 7, going all the way up to 14. To find the pH, we use this formula. Make sure you highlight this in your notes or draw a box or an arrow or something. pH is equal to the negative log of these brackets here. You might want to write in your notes. Mean concentration of, so maybe molarity, okay, of hydronium here. So the higher the concentration of these hydronium ions, the more acidic the solution, and the lower the pH. That has to do with this logarithmic relationship here. Some of you have had more experience with logarithms than others. I'll just tell you this. Logarithms are basically the opposite of an unknown exponent. Or what? Yeah, it's basically how you find an unknown exponent. If there's nothing written at the base here, it means base 10. So what log of a number means is that 10 to some power equals that. So if you're finding the pH, you're basically finding 10 to what power is this concentration. And of course, don't forget the negative sign here. All right, on your calculators, be careful. Sometimes with older calculators, you need to plug in the concentration first, then hit log, then hit plus minus. Newer calculators, you can plug it in just in straight order. So let's look at an example. What is the pH of a solution if the hydronium concentration is 0.001 molar? Well, like we saw before, just plug that into the equation. pH equals negative log of the concentration here. Put in 0.001, you get, oh, don't forget, yeah, negative and log, and you get 3. And that makes sense because 10 to the minus 3 is 0.001. This makes sense because it's a fairly high concentration of hydronium, and therefore we have a low pH and acidic solution. This isn't quite something deadly. This is only the pH of something like soda, for example. Okay, now also notice the units disappeared here. It's hard to take the log of a unit, and so therefore pH is one of those rare situations where they're allowed to run around naked. It's like the number nudist colony. Just remember, concentration has units, molar. pH does not. Okay, at this stage, I'd like you to plug this into your calculator. Make sure you get 3, and then you can pause to do some practice problems. Okay, give those a shot. Okay, now I don't have your answers written here, but what you should notice is this. When you've completed these, each one has a decreasing concentration of hydronium. Therefore, your pH should be increasing. Should range somewhere between, I think, 2 and 8, if I remember correctly. Okay, so let's look at the opposite now. What if we want to find the hydronium concentration and we're given the pH? Well, if you look at your calculator, there's actually an inverse function above most log buttons, and it's 10 to the something, 10 to the x, for example. That's because this does the opposite of what log does. So if we're trying to find the hydronium concentration for a solution with this pH, 6.1, simply plug it into the formula. Take 10 to the negative 6.1 power. Please make sure you include this negative here, because otherwise you're going to get a very large number. Something like 10 to the 6 or something, and that would be a really high concentration. Remember, a mole is a handful, a liter's 2 water bottles. So you're going to tell me, let's see, if you plug into the positive 6.1, you get, you know, 1 million. You're going to tell me you could fit 1 million handfuls in 2 water bottles? I don't know about that, man. So anyways, you should be getting a relatively small number of negative exponents. Very common for the concentration of hydronium here because it shouldn't have a high concentration of hydronium. This is a nearly neutral solution. Okay, now is the point where you pause your video again so you can do some practice problems. Find the concentration of hydronium for each of these solutions. Okay, so what you should notice, if you got the correct answers, make sure you had units of molar on each one. You do want those units here, no naked numbers for these. And what you should have also noticed is as we have an increasing pH, we should have a larger negative exponent or a smaller concentration of hydronium, because the less acidic the solution, the less hydronium ions in that solution. Now you might ask yourself, why is there any hydronium at all In this solution, the pH is over 7. That should be a basic solution. Well, what you have to understand is that even in neutral solutions, we do have a small amount of hydronium and also a small amount of hydroxide. In water, 1 out of every 10 million molecules or so will ionize. The hydrogen off of water will jump off of one to form a hydronium and a hydroxyl, but if they're present in equal amounts, the solution is neutral and the pH is 7. We'll discuss more of that later. For now, let's add one last little piece, and that is the concept of titration. Titration is the method we use to basically determine the molarity of a solution that we don't know its concentration. Remembering that acids and bases neutralize each other, if we can measure that pH in some way and get to an endpoint where we have equal amounts of hydronium and hydroxyl, then we can do some math to determine how much or what the unknown concentration is. Here's a basic chemical equation, sorry that arrow is a little low, of what I mentioned before, hydronium and hydroxyl. When they get together, it's just water. The extra hydrogen here jumps over here, and what do you have? 2 water molecules. So this is what you guys are going to be doing on the lab Friday. Hope you enjoyed.